Okay, guys, again, it's 13th January. In the event that you're watching this from home, we are working on this stuff today. And so my lesson plan for this particular hour, we are going to be looking at Newton's second law in terms of momentum and then solving some impulse momentum related kinds of problems. Let's go ahead and jump at it. Those of you that, seniors, raise your hand, class of 25. Next year, juniors, you guys are class of 26. I had this young man, his name's Tyson Zimmerman, and I asked him if I could give him credit for this statement. He graduated in 23, so I had him in my one semester class like 3 or 4 years ago. And when I was talking about momentum and its connection to force, he's like, so momentum is sort of like potential force, sort of like potential energy. And it's very clever. He wanted to be an engineer. He might be in the engineering school right now, but if he wanted to be an engineer, I told him you really should have been in my 4-year class like this, because this is where you get into the heavy duty stuff. And but he's a really smart kid. He holds the record for the best ME score for an egg drop device. He's very clever in how he designed it, and so he holds the record for that. So anyway, he's like, it's like potential force, and it says very clever. He allowed me to put his name up there. I want to show you what he meant by that. And so let's write Newton's second law in terms of momentum. Many students, by the end of the semester, they say Newton's second law was the most challenging to work with, all the FBDs and all those kinds of things. I'm going to try to make that simpler by looking at it in terms of momentum. So I'm going to replace the A with delta V over T. So that's just a substitution. Now I'm going to do a regrouping. I could write it as sum of the forces is equal to M delta V over T. So all I'm doing is I'm regrouping that. So the associative property of multiplication division stuff, I can choose to associate the delta V with the M as opposed to the delta V with the T. So it's just rearranging some things. Those of you that recognize the numerator as change in momentum, M delta V is just equal to change in momentum. And I can see that force is actually equal to what's called the rate of change in momentum. So Tyson was like, so force is like, or momentum is like potential force. And I'm like, well, momentum does involve force, but it's not the same as force. It's the rate of change in momentum. And so force is equal to, instead of saying F equals M times A, we can say force is equal to the rate of change in momentum. How quickly does the momentum change? That is how we can talk about force. Now, I have a rocket engine here that is going to be acting on either a really lightweight rocket or a very large, massive rocket. One of the things I'm going to look at with you guys today is model rockets and sort of look at the engine powers on those things. I'm going to ask you guys to, as a review for your exam, that amount of force acting on a small mass versus that amount of force acting on a large mass. Will you draw for me what you think velocity time graphs will look like for the lightweight rocket and the heavyweight rocket on here, assuming a constant force? This is meant to be a review for your final exam. Can you associate changes in velocity graphically using F equals M times A? Take a moment, see if you can do it. If you're trying this from home, watching the video from outside, you should try the same thing. Draw a dashed line for the heavy massive object and a solid line for the lightweight object. What would the velocity time graphs look like? Once you have it, will you share with that person that you're sitting next to? See if you agree with that person. What do they look like? All right, it looks like we have everyone's tried it. Let me show you what they should be looking like. The dashed line should be a fairly shallow slope. Recognizing that that's got a lot of mass, it's not going to change its velocity very quickly. The solid line should be steeper, and the slope of those lines would represent the acceleration. Same amount of force acting on each object would cause different amounts of acceleration because they have different masses. Now, if I were to ask you to change or graph the momentum as a function of time, we know that this one's going to increase its velocity fairly quickly. So after a certain amount of time, that object will be traveling faster than this one. graph of their momentum look like as a function of time? Try that one and see if you can visualize what this equation is saying in terms of their momentum. Try that. If you're watching this from home, you should try that as well. Newton's second law is basically saying F is equal to the rate of change of momentum. Each of these graphs would be identical. The solid and the dashed line would be right over top of each other. The idea there is that what force equals is the rate of change of momentum. So it doesn't matter how massive that object is, they should acquire equal changes in their momentum. The small lightweight one is going to be traveling faster than the heavier one, but if I look at them in terms of their oomph, they're both going to acquire the same oomph because they're both acting on by the same amount of force. So force is equal to the rate of change of momentum. Now, I'm going to show you a couple of other things to try to connect forces with time intervals. You might remember my story of Tony, the guy that I played basketball with who missed that layup and he hit his hand against the wall and broke his fist. Tony had a really large fist that he could throw really fast, which means that he could develop a lot of momentum in his fist. Boxers will often use the momentum of their fist to be able to knock out their opponent. Why do they wear gloves, do you think? Why do boxers wear gloves? It changes the rate of, it makes the rate of change in momentum of their fist smaller by making the time interval bigger. So the idea there is that gloves are time extenders. Which, because of the fact that force and time change momentum, which means that they are force reducers. Bare knuckle boxing often involves people breaking their hands, just simply because the amount of force acting during that collision is really, really large. And so gloves are time extenders, force reducers. Okay, so if I can make the time interval bigger, I make that force smaller. Now I'm going to show you that with an equation, reformulating Newton's second law again. This time when I go to write this, I'm going to move that time around to another spot. So F equals m times a, I'm going to write that as F is equal to m delta v over t. Except now what I'm going to do is I'm going to multiply time by both sides. And I get an equation that looks very similar to the work energy theorem. This is now what's called the impulse momentum theorem. So it's not work energy, this is impulse momentum. The left-hand side is what we call impulse, force acting through a time interval. Force acting through a time is equal to mass times change in velocity. Another way to say that is impulse, which is the product of force and time, is equal to the change in an object's momentum. Now, I'd like to take a moment and refresh for you what we just got done talking about with the work energy theorem. So I want to do a compare and contrast. What we just got done talking about is force acting through distance was equal to delta KE. What this one is saying is force acting through time is equal to delta P. These two theorems, one's called the work energy theorem, the other's called the impulse momentum theorem, are key to understanding these conservation laws. So instead of combining force with the distance, we're going to combine force with the time value. Force, again, makes objects change how they're moving. We can either combine force with the distance or combine force with the time. One changes kinetic energy, the other changes momentum. Now, let's do some more concept building. The equation force times time is equal to delta P shows that force and time play inverse roles. If the product of two things is a constant value, then increasing one will decrease the other. So for a given delta P, if the delta P is a given value, the car is going to come to a stop either by hitting its brakes or it's going to come to a stop by hitting a tree. For a given delta P, increasing the time interval will make the delta P, during which the delta P occurs, will lessen that amount of force. So making T bigger makes force smaller. Applying the brakes, that brake provides the force for a very long time, which means the amount of force acting can be small. If I hit a tree, that force is going to be really large because the time interval is very, very small. Now, folks, when we did F equals m times a, you guys did this kind of stuff. It's just acceleration itself can be somewhat confusing. This is looking at it in terms of momentum. All three of the things on the left are about time extensions. So let's review those for a moment. When you guys built your egg drop device, your goal was to make the time interval bigger to be able to make the force smaller. So you guys essentially provide a time extension for the egg. If it hits the plate, it's going to come to a more rapid stop, so it requires a much larger force. If it hits the pillow, it comes to a much smaller or much slower stop, so it has a fairly small force. Do you guys know why they put the pea gravel and the wood chips and stuff underneath the playground equipment? Do you guys know what they're doing? Same idea, making the time bigger to make that force smaller. The demonstration I'd like to do with you involves rock climbing, and I don't know, anyone in here done any rock climbing? Anyone here interested in rock climbing? A few people? Okay. Are you actually a practiced rock climber? Do you have equipment and stuff like that, or have you just done it? Okay. So my daughter is a big-time rock climber now. She learned it in college, and she's continuing to do that. So she goes down to the Kentucky area and does all this stuff. So I talked with her quite a bit about this. She wants me to try it. I don't know that I can actually do rock climbing at this point. But the ropes that they use often have a little bit of give to them. Has that been your experience, that they have a little stretch to them? So what I'd like to do is I'd like to show you the importance of that stretch as far as making the amount of force smaller. Now, this is what you might call top climbing. Top climbing is where you sort of get ahead of the rope. So you're always gonna lock in to whatever kinds of things they put into the rock to try to arrest your fall in case you fall off that rock. But if you're top climbing, then what that means is you're going to be ahead of wherever that rope is. You always have to be anchored to another spot, but if you fall from here, you're going to fall until that rope is going to arrest your downward motion. Of course, the goal is you want to make sure that you stop with the rope before you hit the ground. But you also want to make sure that the rope gives a little to make that force smaller. Now, I'm gonna pause this thing here. If you can give me a second. Demonstrations do not work well on video, so I'm gonna